Okay, so the question that we want to answer today, or not today, but for this video, is why are we so interested in the cosine and sine functions? So definitely part of what we're interested in is the orthogonality properties. Okay, because why are we interested? So let's just take a step back and ask, why do we care about orthogonality to begin with? And it's very simple. It just allows us to compute the coefficients. So if I have a sequence of orthogonal functions, and I know that one function is written as a linear combination or an infinite series of those orthogonal functions, it's very simple to determine what the corresponding coefficients are. Okay, so let's actually take a step back and even think about what orthogonality means in our context. So let's say we have two functions find on the interval 0 to L. They are orthogonal if their integral from 0 to L f of x g of x dx equals 0. Okay, I'm going to move this down to kind of center it because I don't want to go so far over that way. So they are orthogonal if the integral of their product is equal to 0. So the integral from 0 to L f of x g of x dx is equal to 0. And hopefully you remember from a linear algebra class, there's a reason we call this orthogonal. This integral pairing is something known as an inner product. This is known as an inner product. It is a generalization of the dot product. And what does it mean in terms of a dot product? What does it mean when we say two vectors? If we just think about Rn, what does it mean when we say two vectors are linearly independent? It means their dot product, orthogonal. It means their dot product is equal to 0. So equivalently, if we have two vectors in a function space like what we have here, we say they are orthogonal if their inner product is equal to 0. And furthermore, let's say we have a sequence of functions, phi k, they are orthogonal if the inner product of phi k and phi l is equal to 0 for k, equal to 0 for k not equal to L. And what is the inner product? It's just this thing right here. Okay, now notice that we can slightly generalize this notion of orthogonality. Instead of just integrating with a weight of 1, we could integrate with a weight of sigma of x dx, where here sigma of x is some function that's strictly greater than 0. Now, we haven't seen anything much like this in our class, except remember what we're actually doing. The integral that we care most about is not the integral of f of x times g of x or f of x times the cosine or sine. It's 2 over L times that. And so what we can do is we can move this 2 over L to be over here, and we can write it as 2 dx over L. And here we're kind of thinking about having a weight sigma of x as being equal to 2 over L. Okay, and so similarly, we can say that f and g are orthogonal with respect to this weight, this 2 over L times dx weight. And we can actually even make this definition a little bit better, or think about functions that have even a little bit better properties. We can say that phi k are orthonormal. Okay, hopefully these words are not brand new to you. We can say they are orthonormal if this inner product is equal to 0 when k is not equal to L, and is equal to 1 if k is equal to L. And so the primary example that we've seen in this class are going to be the cosine and sine functions. So example if the phi k's are equal to cosine k pi over L x, so they're equal to these cosine functions, these are orthonormal ON relative to the inner product fg equals the integral from 0 to L f of x g of x 2 dx over L. Okay, we've already seen that. Okay, if I have a cosine and a sine that aren't the same, this integral is going to be equal to 0. If I have a cosine and if I have two different cosines that have a different value of k, it's going to be equal to 0. If it's the same value of k, then it's going to be equal to L over 2, and then you multiply by 2 over L like it's 1. Okay, if you're unsure about what I'm saying here, verify that what I'm saying is true. That if we look at something like the integral from 0 to L cosine k pi over L x cosine L pi little L pi over L x 2 dx over L, this is equal to 0 if k does not equal to L, and it's equal to 1 if k is equal to L. Let me get out of the way so you can look at it. Okay, so what we have seen is that the functions, and the same is true for sine functions as well. And here's an exercise, or here's two exercises. One, write down what statement is true for sine functions. It'll basically be the same exact thing, except instead of cosine functions, it'll be sine functions, but it's a good thing to do. And second, what would be the orthonormal basis that we've seen on the interval minus L to L, and what is the inner product going to be? There's going to be two changes that we have to make over here. Okay, so why do we care about orthonormal functions? So we haven't gotten yet to why we care about sine and cosine functions. But why do we care about orthonormal functions? So what's important about that? So why orthonormal? So why orthonormal? Well, for the following reason. If I know that f of x can be written as a series, it could be either a finite sum or an infinite sum of these functions, ck, phi k. So if I know that I can write f as an infinite or as a finite or infinite linear combination, again, you shouldn't say infinite linear combination, but I like it. So if you can write f of x like this, then we can easily compute the ck coefficients. And we've already seen this with sine and cosine functions, but let me just go through this kind of more abstract framework with inner products. So if I look at the inner product of f and let's say a phi L, well, what am I going to get? Well, f is equal to this. So I'm going to get ck phi k phi L like this. Okay, and notice this notation right here is a little ambiguous, or I'm claiming too much. So when I say f of x is written like this, what this means is a pointwise inequality. It means if you plug in an x, these two things are the same. But on the level of functions, what we really want to say is something more like this, that f is a series of these phi k functions. Okay, and so it doesn't really matter, we're saying that these two things are equal to each other. Okay, taking out the x just makes things a little more precise, actually. And I'll explain what that means in just a moment, or why I say it's more precise in just a moment. Also notice I'm purposely not putting any index here, because the indices could go from minus infinity to positive infinity. It could go from minus 5 to 17, or anything like that, anything at all. Alright, so now this, using the linearity of the inner product, this is equal to the following. And again, this should be very familiar from your linear algebra class. This should be a review. And if not, just think through what I'm doing here. Maybe I'm skipping a couple steps going from here to here using the linearity. Okay, but now what I'm going to get, now what am I going to get? Well, this is going to be equal to 0 whenever k is not equal to L. So the only non-zero term is going to be corresponding to k is equal to L. Okay, and in that case, the inner product is going to be equal to 1. So this is just equal to CL times phi L times the inner product of phi L with itself, but this is just equal to 1. So this is just equal to CL. And so now we have CL is equal to this. CL is equal to the inner product of F with phi L. Okay, so I'm about to erase all of this. So then what this tells us is that if we can write F in this way, then the CKs have a very nice formula. It's this inner product like this. Okay, this is a very convenient formula to work with. It's how we were able to solve boundary value problems, to find the coefficients in the boundary value problems. But so far, this is true for any, we've said things that are true for any orthonormal set of functions. For example, if you look the Wikipedia orthogonal polynomials, this is an area of research that studies orthogonal polynomials on an interval. And you might remember from your numerical analysis class, if you took one, that you might remember from your analysis class that any continuous function can be approximated well by polynomials. And most functions can be approximated by continuous functions. Therefore, we can approximate functions well with polynomials. But the monomials, like 1, x, x squared, x cubed, and so on and so forth, these are somehow bad for numerical uses. But orthogonal polynomials might be better for numerical cases, for use in numerical computations. And you can read more about that or recall from your numerical analysis class. Okay, so what we're saying is if we can write F as a linear combination, either a finite linear combination or an infinite linear combination of these orthogonal functions. I feel like every time I say infinite linear combination, I just need to point out that a lot of people don't like that term because I'm doing this lesson partially with my door open. I don't want a colleague to come by and yell at me. Okay, so if we can write F as a infinite or as a finite or infinite linear combination of the phi k functions, then these are the formulas. Okay, but let's ask this question: what if we can't? What if we can't write F as a series of phi k? Okay, I mean, one answer is just, well, we can't, so we're not going to do it. But the other thing that we can think about is, then what is this going to be equal to? See, we can compute this as long as the inner product is well defined, and it is. We can compute this. So what is the relationship to this and F if I know that I can't write F in this way? So what is this equal to? Like, what does this have to do with F? Like, how is this related to F? Is it just something that's completely different from F, or is there some relation to F? And it turns out that this is something called the projection of F onto the functions phi k. Okay, if you remember from linear algebra and orthogonal projections, if you have a subspace spanned by some vectors, and you get an orthonormal set for that subspace, the best approximation of a vector, so if you take another vector and you want to approximate it as a vector in this given subspace, this is going to be the formula for it. It's called the orthogonal projection. So this function right here is the best approximation This is a best approximation to F by functions by the functions phi k. Okay, and again, formally, this is exactly the same as doing an orthonormal, or sorry, this is exactly the same as doing an orthogonal projection of one vector onto a subspace of other vectors. So again, recall that I want you, if you don't remember this from linear algebra, I want you to try to remember it. Okay, but what do I mean by best approximation? So what is best approximation here? Well, what it means is that if I want to minimize, find the g, so find the g, minimize the g such that g is equal to a linear combination of the phi k's. So I want to minimize the following thing, the integral of g minus f squared going from 0 to L, 2dx over L. So I want to minimize that. But if I want to write this kind of more generically, I can just write this, or not more generically, but more, kind of more generically, but I mean using the inner product, I could write this as the inner product of g minus f with itself. Okay, if I want to find the g that minimizes this, g is given by this function here. So the g that minimizes this, okay, so this would be the error, g minus f, so g is in the linear span of these phi k functions, and I want to find the g in the linear span of the phi k functions that minimizes this g minus f quantity. Okay, and let me make this a little less obscure. Let me go back to what I had before. Why is that what we care about? Well, this, if you so again, actually put g minus f comma g minus f in this inner product and show, I mean it's not going to really take a lot, that it's equal to this. Okay, so I want to find the function g that minimizes this. Okay, this is literally the least squared solution. And the function g that minimizes this is the projection. So if I want to find the g that minimizes this quantity here, g minus f, so g again is in the linear span of the phi k's, f is a function I want to approximate. I want this to be as small as possible because this is the error between f and the approximation, or we call this the L2 error between the f and the approximation. L2 because we have a 2 there. Okay, and so the g that minimizes this is going to be given by this formula here. And so in particular, if I want to look at the case, let's say I want to look at the case where I don't have an infinite set of my functions. Let's say I'm looking at the sine case. I have k goes from 1 to n for some positive n. And so I just look at the first, let's say the first n basis functions for the sine functions. So in other words, I want to because in practice we can only approximate with a finite number of these things. So then the projection is going to be like this, defined from k equals 1 to n. Okay, and so this would give us the best approximation to f using the first n sine functions. Okay, so I just explained why we care about orthonormal functions. So that's part of the reason that we care about sine and cosine functions. In the next video, I'm going to explain, one, why we particularly care about sine and cosine functions for this class and not other orthonormal sets. And I'm also going to use the fact, so hopefully you know by now, the reason we care about sine and cosine functions is because that's what comes up when we look at boundary value problems, and those come up when doing separation of variables. So I'm going to say, okay, using the fact that we know sine and cosine satisfy these boundary value problems, I'm going to use that to show that they are orthonormal. So I'm not just going to compute the integrals, like a product of sines and using antiderivatives and stuff like that. I'm going to say, given the fact that sines and cosines satisfy these particular boundary value problems, that will imply that they are orthogonal to each other. And in particular, orthonormal as long as we define the inner product with the 2 over L here. Okay, but that's it for this video.